And welcome to this video. In this video, we'll be covering matrices for A-level and the basics of matrix operations. Let's get started. What is a matrix? A matrix is a rectangular array of numbers or algebraic expressions arranged in rows and columns. It can be represented using a capital bold letter, such as a capital bold A. Think of it a bit like a data table. Here is an example of a matrix. The dimensions of a matrix are given as number of rows by number of columns. Here is an m by n matrix with m rows and n columns, thus giving it m by n dimensions. The matrix A displayed here is a 2 by 2. Now let's cover some special types of matrices. The first of is the null or zero matrix. All of its elements are zero and it can be of any dimension. Here are some examples of null or zero matrices. Now let's cover the other type that you'll need to know, which is the identity matrix, which is sometimes represented using the capital bold letter I. It has ones on the leading diagonal and zeros in all other element positions. An input matrix times by the identity matrix will return the original matrix. This is because the matrix is by definition the identity of matrix multiplication, which means whenever you use an operation on a certain mathematical input type, the identity will cause the original input to be returned. So for matrix multiplication, the identity matrix causes the original matrix to be returned, and thus it is the identity matrix for matrix multiplication. The identity matrix can be any square matrix, but any dimension square matrix. So it could be 4 by 4, for example. And in order to use the identity matrix appropriately, you must multiply this identity matrix by any appropriate matrix, as we'll see later in the lesson. Here are some examples of identity matrices with their leading diagonals labeled. So as you can see, the main diagonal with ones on the lead diagonal. Let's now go through one of the basics of matrix operations, which is matrix addition and subtraction. In order to do this, it is relatively straightforward. You add or subtract the corresponding elements of the two matrices. In order for the operation to be valid, both matrices must have the exact same dimensions. If this is not met, then the matrices are not conformable for these operations. Let's now go through an example of matrix addition. Here we have matrices A and B, and we will see how they are added. As you can see, each corresponding element is being added together to form a matrix of the exact same dimension as the original two matrices. Now let's go through matrix subtraction, which is a very similar procedure, except instead of addition, we do subtraction. And again, it produces a 2 by 2 matrix. Let's now cover scalar multiplication of matrices. For this, it causes all elements in the matrix to be multiplied by a single number, i.e. the scalar. It is represented using the scalar next to the letter of the matrix, and there are some examples here. Let's cover how this is done. We'll define matrix A, and we will times it by 2. And similar to matrix addition and subtraction, it produces a matrix of the exact same dimension, simply with all of its elements multiplied by the scalar. We will now cover a different matrix operation known as matrix multiplication. In order to do this, you can multiply matrices of same or differing dimensions, but the number of columns in the first matrix must equal the number of rows of the second matrix for this operation to be valid. Mathematically speaking, if the first matrix has dimensions n by n and the second has dimensions n by p, it produces a matrix of dimensions m by p. Let's look at some examples. In this example, matrix multiplication is not defined, since the number of columns in the first matrix, 1, is not equal to the number of rows, which was 2. But in this scenario, they are compatible, because 2 equals 2. When we are doing matrix multiplication, to find the value of the element in the mth row and the nth column of the resultant matrix, we select the mth row and the nth column of the first and second matrices respectively. We should then take the dot product between these two quantities, i.e. multiply respective elements and add their products. Don't worry if the dot product doesn't quite make sense to you yet. It is a mathematical term and we will explain this more simply through an example of matrix multiplication. We'll define the matrices and then try and find each of the elements in the resulting matrix. To find the first element in the top left corner, we should select the first row of the first matrix and the first column of the second matrix. For each element we are evaluating, we go from left to right for the row and up to bottom for the column. And we times respective elements together. As you can see, the left element gets multiplied by the top element of the column, and the right element gets multiplied by the bottom element of the column, in this scenario at least. In this scenario, it produced a 2 by 2 because we had two 2 by 2 matrices, which of course the first matrix shares the same number of rows as columns for the second matrix, and because it was 2 by 2 and another 2 by 2, it produces a matrix of 2 by 2 via the formula we showed in the previous slide. Now let's try and see what happens if we do the opposite way round, with the matrices flipped. And it seems as though they're not producing the same answer, which is interesting, because we know that multiplication of numbers, regardless of which way around they are, produces the same result. Matrix multiplication here is done in the exact same procedure, selecting the mth row and the nth column depending on which element you want to evaluate. On to the properties of matrix multiplication. From what we saw previously, BA was not equal to AB. This is unlike regular multiplication, where you can multiply in either order and the result will end up being the same. If the input order does not matter when performing an operation, we say the operation is commutative. Thus, because order mattered in this scenario, matrix multiplication is not commutative. There may be some scenarios where AB does equal BA. In these scenarios, we say multiplication is commutative for these matrices. We can say that matrix multiplication is associative. But what does this associative mean? An operation is associative when operating more than two inputs using that operation. And when doing this, regardless of which order they are grouped in, the result is the same. In this scenario, it would mean that if we multiplied B and C first, and then multiplied by A, it would be equal to if we multiplied A and B together, and then C to get a result. And of course, this only holds if the dimensions fit. Final property of matrix multiplication: if we multiply a matrix A n times, it can be represented as A to the power n, which should seem relatively intuitive. Let's now cover the final operation of this lesson, the transpose. Transposing a matrix causes its rows to become columns and its columns to become rows. The mth row becomes the mth column, and the nth row will become the nth column. When doing this transpose, the dimensions are changed from m by n to n by m, and the transpose works for all dimensions of matrix. Transposing a matrix twice just returns the original matrix. So if you do it twice, it will return the original matrix A in this scenario. And note that this t to the power is the notation for transpose effectively. Here are some examples. We have a 3 by 1 matrix here, and its transpose is 1 by 3. And likewise, for the 2 by 2, it will remain 2 by 2, but look, the 3 and 2 have flipped. Thank you all for watching. In this next lesson, we will be covering the inverse matrix and determinants. Feel free to ask any questions in the comments, and I hope to see you in the next lesson.